So, good morning. Welcome to Krishna's classroom. We continue with our discussions on inner product spaces. Next, we look at the class of linear functionals defined on the dual space of a finite dimensional inner product space. And this is what is called the second dual. And what is the relationship between the given space and the second dual? We explore this in detail. So, let us start with the preliminaries. Let X be a finite dimensional inner product space over it could be a linear space over the field C or R, but I think we will consider on C because we assume equal to N. Now we know that being an inner product space, there exists an orthonormal basis. So we choose one orthonormal basis. In fact, there are several orthonormal bases possible. We choose one of them. So let for X. That is, we have the inner product of xi with xj delta ij standard notation. Now you look at the vector space of all linear functionals over X and denote it by X prime. X prime then we know that dimension of X prime equal to N. And in fact, we shall choose the dual basis xn prime X prime with the property that is xi prime maps xj to delta ij for I 1 to n. Such a basis exists. Now we use the representation theorem. Using the representation theorem, by the representation theorem, is represented by x prime itself, x prime or xi itself, that is, we have so we have the x prime. Now we'll talk about the more detailed structure of this soup. Now you see that the inner product on x induces an inner product on x prime and makes it a inner product space. And we shall such that if x if y1 and y2 represents y1 prime y2 prime respectively. I am just invoking the representation theorem, namely, let me write here x yi prime yi prime of x equal to inner product of x with yi. It is in this sense that then the induced inner product on x prime is given by or I will put it use this y1 prime y2 prime equal to y. This is the induced inner product, and with this x prime is also an inner product space. That is, let us denote this by so x star is essentially x prime, that is the vector space of all linear functions over x with the inner product y1 prime y2 prime defined as inner product of y2 with y1. Now this we have already discussed, and you know that such a inner product is well defined and everything is fine. Okay. So this is denoted by x star. So now we have x and x prime and the important factor is that every element of x star is represented by uniquely by some vector in x. Every in this sense, y prime of equal to y prime belongs to y prime belongs to x star comma the representative y belongs to x. So this is what the representation theorem says. Okay, right. Now we go to the next stage. Likewise, let x double prime x prime prime, that is the space of all x prime. Now x prime is an inner product space. X prime redesignated as x star is now an inner product space. So let x 1 double prime and you know that x star x double prime is indeed an n-dimensional vector space over C or R. And now we have the dual basis x1 double prime, x2 double prime, etc., xn double prime. Okay? And prime. Now one observes that in x star, x1 prime, x2 prime, etc., xn prime is an orthonormal basis. So we will just make an observation of that. Now, we have an orthonormal basis or x star. That is clear. Now what next? We can continue the arguments. Arguments similar to the relations between x star to x star and double prime. So x double prime is the collection of all linear functionals over x star, and we have clearly you have xi double prime psi. And there is the induced inner product x prime prime defined by right. And this indeed defines a inner product on x double prime. So what do we have? We started with an inner product space x. We have x prime and there is the induced inner product. Once again you have x double prime and the induced inner product. And they are all related. So the inner product on x induces or makes x prime an inner product space. We called it x star. And then further the x double prime is also made into an inner product space called x double star. So let x double star. What we have is this, that y double prime where y prime is the representative of y double prime and which is again equal to y is the representative of y prime, x is the representative of x prime, and this is the inner product in x. So if you want, you can write here x prime, okay, and the consequence is that this is on x prime prime, this is equal to x prime, which is equal to x. That is how the inner product goes, are related. So I just put sub x prime, sub x double prime to just indicate that the notation is transparent in the sense that this corresponds to inner product of x double prime, this is the inner product of over x prime, and this is the inner product of x. Therefore, now we have three spaces, namely from starting from x, you have x prime, and which we made into x star. Then you have x double prime, which we made into x double star. To make some investigations on this. Okay, so what do we have? Suppose we take x star star, then where x is a unique y prime belonging to x star. So there is the association between these two. That is uniquely determined. Okay. And then what more you have? See, y prime is a linear functional on okay, so here x prime x star. Okay. Now further, x given by this is of course, now this is of course x prime. Okay. So what does this do? This associates with y prime a vector 1. Now we shall define certain functions. Okay, what are the functions? So we started with x double prime. So we have x double prime, y prime, y double prime. This is mapped to y prime belonging to x prime or x star if you want. Okay. Then you have this map to x. Okay. So I can put here x star star. I am assuming all the necessary structures then. Yeah. So this is a picture that you have. So corresponding to y double prime, there is a unique y in X. Okay. And let us denote this by certain maps. So we have phi, let us designate this by phi and this by psi. So phi is from X. And now what you can prove, or what we have proved by the representation theorems, is that this is a one-to-one, both these are one-to-one onto maps. Both one-to-one from their respective domain though. So this is a bijection. This is also a bijection. But both phi and psi are not linear. This is psi. Not linear, but conjugate linear. It is enough to prove that one of them is conjugate linear, then the other can be proved easily. How do you prove that? Okay, so let us investigate this. So let us prove that we will work with the So let us prove that psi is conjugate linear. Okay. So what do we have? We have proved that psi is conjugate linear. So we start with a y prime in, okay, so what we have? We have psi of y prime equal to y. This is what you have, okay, and they are related by the relation that y prime, okay, okay. This is what you have. Let's work on that. So what you have is that if you have a y1 prime, there is a y1. Okay. So we have, let x star and x respectively. So what do we have? So phi psi of so corresponding to y1 prime, there is a uniquely determined y1. Corresponding to y2 prime, there is a uniquely determined y2. Okay. So let us work on this. Now you see that this is how the representation comes. Now let us calculate this. Alpha 1 y1 prime plus alpha 2 y2 prime. This is equal to, yes, what you have is this alpha 1 which is equal to y2, and this you can write, you can take this alpha 1 and alpha 2 inside. Of course here we have got alpha 1 alpha 2 belonging to C or R. Therefore this is equal to which is equal to x alpha 1 conjugate y2. implies this is true for every x. Psi of this is equal to, represented by this, alpha 1 bar which is equal to psi of y1 prime plus alpha 2 conjugate psi of the psi is, so psi is not linear, especially if you keep the, it is linear when you have the associated field R, but otherwise linear. Okay. Therefore, so this indicates that psi from but conjugate linear. Similarly, phi from is not linear, conjugate linear. So what they preserve the conjugate structure, okay, but are conjugate isomorphic. We shall say. So we shall say that they are conjugate isomorphic, not isomorphic, because they are not linear, but they are conjugate linear. Now this is something very, very important. Okay. But now what happens? So you have, see, for instance, you have this picture. What do we have? We have phi here, we have psi here. Okay. What is that you have? You have y double prime is mapped to y prime is mapped to y. Okay. So this is the structure that you have. Now what do you do next? Therefore, you see that this both phi and psi are conjugate isomorphism. That means they are one-to-one and on-to between the respective spaces. I mean, there is no problem about it at all. Okay, so you can talk about their composition. Now we see that psi composition phi is a map from X. Phi carries y double prime to y prime and then psi carries it to X. Okay. What about this particular map? Okay, you can show that. See, both psi and phi are individually conjugate linear maps. Okay, therefore, what about psi composition phi? Well, let us work on that. So one could easily verify that this is an isomorphism between X double prime and X. It's easily verified that psi composition phi is an isomorphism. How do you prove this? Okay, let us take psi composition phi this is equal to psi of alpha 1 conjugate y1 prime which once again you work on this, you see that this is equal to alpha 1 y1 plus alpha 2 y2, we have alpha I double conjugate equal to alpha I. And this in turn you can write alpha 1 psi composition this is equal to okay. So we have a linear map from x double star to x, or you can say that x double star is isomorphic to and this is how it goes. You have got y double prime to y prime to y. Okay. Now, this is the map that you have. So, this is the connection. It's a linear map. Whereas these are not individually linear maps. They are conjugate linear maps. Okay. So this phi composition psi is a natural isomorphism between x star. X. And what you have is this, that x double prime y double prime of x star star, this is equal to y prime x prime of x star, which is equal to x y of x. This is the connection that you have, and this is the important isomorphism result. Okay. So for each y double prime in x star star, there is a uniquely determined y in x, and this connection is a natural isomorphism, whereas the intermediaries like phi and psi, they are not naturally isomorphic. And one can easily see that, you see, this identification is independent of the coordinate system that you employ to study this problem, because you know that this is after all x star and x double star, x double star, x star, they are all inner product spaces of dimension n, and you know that there are several isomorphisms that you can define between them, because they are all n dimensional vector spaces over C. But this is something that comes out from the representation theorem. That's why you call it a natural isomorphism. Okay, and you see that the natural isomorphism psi composition phi from x double star to x is something very unique. Okay, and that is also independent of the choice of the coordinate system that one uses. Irrespective of what coordinate system that you use to study this particular transformation, you always end up with the same linear transformation, the identification, and therefore it is unique. Now what you have is that of course we have seen that in this case conjugate linear, but suppose you don't have the inner product space structure at all, then you have again similar things with the star replaced by prime, but now you don't have the representation through inner product or anything coming up. There of course what happens is that when x star is replaced by x prime and x star star is replaced by x double prime, then you see that you have the corresponding maps that you can define, and this defines the maps that you define is an isomorphism at every stage, and therefore their composition is also a isomorphism from x double prime to x. But we have already seen that this is not, this is also a from x double prime to x, the map that you establish is essentially a linear isomorphism, which is a natural isomorphism, whereas the maps between x to x prime or x prime to x double prime, they are not natural isomorphisms. They do depend on the basis that you introduce. Okay.